So, friends, let us continue with the example problem, which is lecture 8 in module 1. We will pick up a very simple example to demonstrate this. We will take a 2 span continuous beam as shown in the figure now. Let us say this span is 3 meters and this span is 5 meters. I call this as A, B and C. You can also name them as 1, 2 and 3. So, this is my member 1, member 2 subjected to some loading. Let us say the external loading in AB is an uniform distributed load of intensity 20 kilonewton per meter, and BC has got a concentrated load of 40 kilonewton, which is at the center. The beam has got constant EI and we need to find the reactions and end moments of this beam. So, analyze this beam, okay? That is the problem. So, closely look at this problem first. Support A is fixed, support B and C are simply supported. There may be some unrestrained displacements and restrained displacements. So, we need to mark them first. Let us do that. So, take the beam, let us mark the unrestrained displacements in green. So, fixed end cannot have a rotation. So, this can have a rotation. I call this as theta 1, I call this as theta 2. I need to continuously label the unrestrained displacements first, then the restrained displacements. So, theta 1, theta 2 are 2 rotations which are free at ends B and C. Then the restrained displacements, rotation, displacement and then displacements at B and C. So, this gives me the following hints. The following hints are: there are totally 6 degrees of freedom, out of which 2 are unrestrained, which are theta 1 and theta 2. Remaining 4 are restrained, which are theta 3, delta 4, delta 5 and delta 6. So, this also gives me a very clear idea that my unrestrained submatrix KUU will be of size 2 by 2, because there are 2 unrestrained degrees of freedom, and the total stiffness matrix of the member ABC, the complete beam, will be of size 6 by 6. The element stiffness matrix of AB will be of size 4 by 4, and what will be the labels of that? To obtain the label, let us first compare this with a standard fixed beam. So, this is a standard fixed beam which we said theta p, theta q, delta r and delta s. So, the standard beam. Let us compare this beam with AB. I already said, even though the support B is simply supported, for us the basic element is a fixed beam. Okay. So, therefore, the labels are for the KAB will be theta 3, theta 1, delta 4 and delta 5. Okay. That is, the labels are 3, 1, 4 and 5. Similarly, for KBC the labels will be 1, 2, 5 and 6. Please see the order: rotations and translations, rotations and translations, rotations and translations. Okay, that is how we have done. So, now having said this, we already know for a standard fixed beam with theta p, theta q anticlockwise, delta r up and delta s up, the standard stiffness matrix will have labels P, Q, R, S, P, Q, R, S. We know this is actually 4 EI by L, this is 2 EI by L, these are the two rotational coefficients. Similarly, this will be 4 EI by L and this will be 2 EI by L. We can partition this matrix this way. Remaining all can be derived, we already said that. Adding these two, divide by L, that is 6 EI by L square, and put a negative sign to this, 6 EI by L square. Similarly, adding these two, divide by L, 6 EI by L square, put a negative sign, 6 EI by L square. Then adding these two, divide by L, 6 EI by L square, adding these two, divide by L, 6 EI by L square. Then adding these two, divide by L, 12 EI by L cube minus 12 EI by L cube, and the last column is negative of the third column. So, minus 6 EI by L square, minus 6 EI by L square, minus 12 EI by L cube and plus 12 EI by L cube. That is a standard stiffness matrix of size 4 by 4 by neglecting axial deformation. Okay. We will use this for our problem. Let us say in our case, I want to draw two separate beams and mark the labels. For me, basic element is fixed beam. Let us say AB will have labels 3, 1, 4, 5. So, I should say A and B. So, it should be 3, 1, 4 and 5. Okay. Similarly, for BC 1, 2 and 5 and 6, 1, 2, 5 and 6. Okay. Let us now derive the matrix for KAB, which is EI common. The labels are going to be 3, 1, 4 and 5, 3, 1, 4. So, this is going to be 4 EI by L. Okay, this value is actually 4 EI by L, which I should say is EI is constant. So, 4 by 3, because L is 3 in this case, you can see here span AB, L is 3 meters, okay. So, 4 by 3 which is 1.333 and this will be half of that. So, 0.667, this will be sum of these 2 by 3 again, which is 1.333 plus 0.667 by L, that is 3 meters, which will be again 0.667. This will be minus of that value 0.667 and this will be 1.333, this is 0.667. So, this value will be add of these two, addition of these two divided by L, which is again going to be 0.667 and this is going to be minus 0.667. As far as this value is concerned, this will be addition of these two by L again, which is again going to be 0.667. Similarly, this value will be addition of these two by L again. So, 0.667 and this value is going to be addition of these two by L again, which is 0.445, that is this will be actually equal to 0.667 plus 0.667 by 3, actually 0.445 and this value will be minus 0.445 and the fourth column is just a reverse of this. So, it is going to be minus 0.667 minus 0.667 minus 0.445 and plus 0.445. Let us have this matrix clearly written here. KAB will have labels 3, 1, 4, 5, 3, 1, 4, 5, 1.333, 0.667, 0.667 minus 0.667, 0.667, 1.333, 0.667 minus 0.667, this will be 0.667, again 0.667, 0.45 minus 0.45, this will be minus 0.667 minus 0.667 minus 0.45 and 0.45. So, I have KAB as this. Okay. We can also do this for KBC, the same logic, EI constant. Let us look at the label of KBC. Look at KBC, BC will have labels 1, 2, 5 and 6, 1, 2, 5 and 6, similarly 1, 2, 5 and 6. So, this is going to be 4 EI by L, 1 1 is going to be 4 EI by L. I write this value, let us say it is going to be 4 EI by L, EI is constant, I will remove this, simply it is going to be 4 by L, L is 5 meters which is 0.8 and this is going to be half of that which is 0.40 and this value will be sum of these two by L, that is 1.2 by 5 which is 0.24, this is minus 0.24 and this value is going to be 0.8, 0.4, again 0.24 minus 0.24 and this value will be sum of these two by L, which is 1.20 by 5 which is 0.24 again, this is again sum of these two which is again 0.24, and this value will be sum of these two by L, which is 0.48 by 5, which is 0.096, this is minus 0.096. The last column is simply the negative of the previous column. So, minus 0.24 minus 0.24 minus 0.096 0.096. Let us write down this matrix in a clearer way. EI, the labels are 1, 2, 5 and 6, 1, 2, 5 and 6. The values are 0.8, 0.4, 0.24 minus 0.24, 0.4, 0.8, 0.24 minus 0.24, 0.24, 0.24, 0.096, 096 minus 0.24 minus 0.24 minus 0.96, 096. So, we have now KBC and KAB. Let us write down both of them here, but slightly in a different manner. So, I am going to do this for both of the cases. This is KAB, which is EI times of, and this is KBC, which is EI times of. If you look at KAB, the labels are 3, I am marking them in red because 3 is a restrained degree, then the next degree is 1, which is a unrestrained degree, and then the restrained degree 4, then 5. Similarly, 3, 1, 4, 5. If you look at the labels of KBC, KBC labels are 1, 2, 5 and 6, you can see here 1, 2, 5 and 6. So, out of which 1 and 2 are unrestrained and 5 and 6 are restrained. So, restrained in red, unrestrained in green. Okay. So, let us write down the values. We already have the matrix here. I am just copying the matrix again for our convenience. So, that is for KAB. Similarly, we can do for KBC, copying the same matrix again 0.8, 0.4, 0.24 minus 0.24, done. Okay. If you look at the K matrix in total, there will be 6 degrees of freedom. So, 1, 2, 3, 4, 5 and 6. Out of which there is going to be a cross partition at 2 by 2. So, this is unrestrained, this is unrestrained row, unrestrained column. Okay. So, I call this as KUU. This is unrestrained row, restrained column. This is restrained row, unrestrained column. This is restrained row, restrained column. So, I want to pick up and only write KUU value here, okay, which is EI times of. So, going to be a 2 by 2 matrix. Let us write down that, which will be 1 2 and 1 2. So, from these two matrices let us pick up the values of 1 1. I am just circling them for our convenience. Okay. 1 1 is this value. So, I write here 1.333. Okay. Then I also have this value which is 0.800. Okay. Then I want to pick up 1 2. 1 2 is this value which is 0.4. I want to pick up 2 1. 2 1 is this value which is again 0.4. I want to pick up 2 2 which is this value which is 0.8. So, friends, my KUU matrix is actually EI times of 2.133, 0.4, 0.4 and 0.8. Okay. So, KUU is E times of 2.133, 0.4, 0.4 and 0.8. Let us find KUU inverse, which will be 1 by EI of determinant 5 4 6. I want you to compute this and check, which I will get the values as 0.8, 2.133 minus 0.4 minus 0.4. I can also check that KUU inverse multiplied by KUU should give me identity matrix. Let us do that. So, 1 by EI times of 1.546 multiplied by 0.8 minus 0.4, 0.4, 2.133 multiplied by EI times of 2.133, 0.4, 0.4 and 0.8. If you multiply this, let us say for example, this value is going to be 0.8 of 2.133, okay, minus 0.16 divided by 1.546 will give you 1.0. Okay. This value if you see 0.8 into 0.4 minus 0.8 0.4, this becomes 0. If you look at this value minus 0.4 2.133 plus 0.4 2.133, this will become 0. And if you look at this value minus 0.4, that is minus 0.16 plus 0.8 into 2.133 by 1.546, which will also become 1. So, it is an identity matrix. So, this statement is proved and therefore, this inverse is correct.